Well, thank you so much for having us, first of all. So today we're going to present a topic regarding technologies and platforms for remote and autonomous bridge inspection. And I have great co-presenters, but I will start with the topics as my slide with few words about me is one of the first. Adriana, can you drive or can I move the slides? I don't know.
I can't move the slides yet.
Okay. Oh, so there are a couple slides that actually are more general regarding the privilege of having the webinar as a IAPSI group. And here is a slide, a few words about me. It's actually quite a bit of words, but I think the most important from the slide is to take out that I am currently a visiting professor at Purdue University, but originally I am a professor at Warsaw University of Technology. And one more important thing about me is that I used to be a vice chair of a task group, DG 5.9 on remote inspection. And a lot of topics that we're going to be covered during this presentation was our main objective of the task group. And now the task group is led by Vedhus and
Yasu.
Yasu Narazaki. Sorry. But I'm still very active in the task group. And in addition to that, I'm also leading and co-chairing the Commission 5 on existing structures. Adriana, can you move one more slide? Yes, please.
All right. So maybe I'll go. I'm Vedhus Hoskere. Thanks, Anna, and Maria for kicking things off. I'm the Casper J. Willem Assistant Professor at the University of Houston, and I direct the Structures and Artificial Intelligence Lab. I joined IAPSI actually through participation in the task group 5.9 that Anna was talking about, which was on remote inspection of bridges. In the previous edition, I was a member. In the current edition, I got Anna's job, so I'm the vice chair now, and we call it remote and autonomous inspection of bridges. I'm also part of a task group 5.7 that's on digital twins of existing bridges. I did most of my education at the University of Illinois at Urbana-Champaign, and before that, I got my bachelor's from India from BMS College of Engineering. It's great to be with you here and look forward to sharing some of the work that we've done as part of the task group and other related efforts today. I'm going to hand it over to Adriana.
Hi, everyone. My name is Adriana Trias. I'm an assistant professor at Rowan University. I'm the director of the Strong Tech Lab, where we apply remote sensing for bridge structural health monitoring. And associated director of the Sustainable Facility Center. In the center, we do focus more on BIM applications. I've been, so my first interaction with IAPSI was back in 2019 in the conference here in New York City. And since then I joined IAPSI. Right now I'm an active member of task groups 5.9, 5.7, 5.9, and 5.11. I received my bachelor's degree in Venezuela, where I'm originally from, and then came to the US to Rutgers to do my master's and PhD. And I'm very happy to be presenting here today.
So that slide presents the IAPSI commissions that was already mentioned by Maria, and to find out where we are actually working is the number 5, existing structures. So Commission 5 on existing structure has several task group ongoing. So can you move to next slide, Adriana? Actually, several. It's probably underestimated. We have 11 active task group at the moment. There are a couple that will be completed this year, and there are brand new ones that just started, such as 5.7 digital twins and the 5.11 structural health monitoring of bridges. And most of our work related to this presentation was developed under DG 5.9 remote inspection of bridges. And we successfully completed several objective of this task. So each of the task group has their goals, and they work through the membership and members that are joining the task groups, and it's a very successful way of collaboration from my experience. So now, as a co-chair of Commission 5, we are tracking all of the progress. We are checking, how to help the chairs of those task group to deliver their objectives, and we also try to always update the websites to have every information up to date. But I think the most important is encouraging to do those voluntary work. That through that voluntary work we can exchange our knowledge and then progress, because this is the best, I think, way when we collaborate between different experts and different experience, and we can develop a better product at the end. So one more time, using this opportunity, the TG 5.9 had developed several publications. We are also working on the structural engineering document that is going to be hopefully published this year. We are going through the review process, and I was very happy to be a co-chair on that task group, and now Vedhus and Yasu are leading the task group, and we will be working on it through another period, which is about 4 years usually. It can extend it after we think if it's needed. Adriana is also very key person in the task group. When we were working on structural engineering documents, she was basically leading one of the section, so that was really good, and that's why all three of us will be presenting today, since we were collaborating on those topics. Move forward. So this presentation has a purpose on informing the audience on the technologies and platforms available to perform remote bridge inspection. And at the end of the presentation, you will be able to recognize application and understand the operating principles of the exposed technologies. We will be showing that through our case studies. And the learning objective is to demonstrate how the emerging remote inspection technologies improve damage detection accuracy, reduce labor-intensive field work, and support more efficient bridge inspections. And now I will let Vedhus to continue through a section, or maybe I'm still on. I don't remember. Yes, I'm still on. Sorry. So the content of the presentation will include introduction, briefly technologies for remote bridge inspection. Then we will have case studies, and the finally will be conclusions. After conclusions, we will have follow-up questions just to wrap up everything what we said. Through this presentation, we will try to help you to understand these two questions that are listed on the slide. In particular, what are the remote inspection technologies and platforms, and what are the advantages and limitations of using them? So there will be straight answers to these questions, but also through the case studies, we would like to present you how to use the technologies and platforms, and also what was the key advantage or key limitation through the case studies. Remote inspection technology can be abbreviated as RIPs. So this is important because for the presentation, we will be probably referring to RIPs. And those remote inspection technology include a range of tools used to assess the condition, integrity, and performance of infrastructure assets from a distance. So that means you don't need to be on the structure, you don't need to touch the structure, but you can still use these technologies to perform the task. These technologies enable engineers and inspectors to remotely monitor, diagnose, and manage civil engineering structures. And there are main RITs such as imaging, laser, radar, and sonar. And we will go deeper into that through our presentation. And also looking at the platforms, we particularly will talk about aerial, so UAVs and terrestrial, vehicle-based, but also there are platforms available for submersible. We will not cover that topic, but we will mention a couple advantages of that. How can we use those RITs? So those technologies and platform can be used at different level of inspection, such as basic visual inspection, detail inspection with structural health monitoring, and expertise in non-destructive testing. And here are some examples. I'm not saying that this is all what we can do, but those are some examples how you can approach those basic visual inspection, for example, through the UAVs for damage detection, or you can use satellites such as INSAR for deformation monitoring of bridges, and also onboard technologies for detecting geometry changes in superstructure and substructure. So that's examples, and we will be talking about that through the case studies. The next column is the detailed inspection with structural health monitoring. Sometimes the same technologies or a combination of technologies can be used for more detailed inspection. And again, we have UAVs. So UAVs can be used just for basic inspection, but also for more detailed inspection. And Vedhus will cover that UAVs technologies more and platforms more deeper during the presentation. Laser scanning for geometry change detection. Again, you can use for just geometry exploration, but also we can use it for the change of the flexion under the load. And radar for measuring dynamic displacement under moving loads and estimating model parameters. And the last column is the most advanced expertise and non-destructive testing. And for that purpose, we usually employ terrestrial robots, submersible robots, and also infrared thermography. So those are not standard tools for inspection, but possible to use. And from this list of the expertise and non-destructive, we will talk a little bit more about infrared thermography. So what are the advantages of using RITs and platforms? So first of all, enhanced safety, reduces the risk of hazardous locations. So inspectors don't need to go to very high exposed bridges or some situations when there is the active load, the bridge is still in operation. Also time and cost efficiency when we have decreased preparation time and operating expenses associated with inspection. Also, RITs promote bridge management system by facilitating the transition to digital bridge management system. And last but not least, improved performance prediction, so enables the development of better performance prediction models and also ensuring user safety. Of course, with the technologies, we have also some limitations. One of the biggest limitations is the regulatory constraints. So sometimes we have regulations related to location where we cannot use UAVs. There are some restrictions, especially on the location close by the airports or any military. There are specifically by country and by state different regulations, so it's better to be to verify that before you use UAVs for the inspection. But there's always a way of trying to get the permission. Weather dependence, that's something that definitely provides some limitations, especially strong winds, bad weather, poor visibility may impact the possibility of using the remote inspection or maybe affecting the data acquisition and the data quality. And the underwater challenges, when we have submersible robots, there are situations when there is just not possibility of seeing through the water or using the submersible robots with the water currents. So that's something that definitely can create a limitation of using the platform and technology. I think now it's turn for Vedhus.
Thanks, Anna. So I'm going to talk briefly about some of these technologies that we can use for remote bridge inspection. Specifically, I'm going to talk about computer vision, which deals with making sense of pixels that are captured in images automatically so as to extract actionable information. So we'll go quickly over some basic concepts, and then when we go to the case studies, we'll see how this plays out. But essentially, what we're doing is we're using different parts of the electromagnetic spectrum. We have some illumination. So when we have passive illumination, it's usually the sun that is illuminating the bridge. And then, of course, we can take pictures with different types of cameras to create images. When we use electro-optical cameras, like what you have in your smartphones or GoPros or other DSLRs and commonly used cameras, then you can get typically 3-channel images where each channel corresponds to a different part of the visible spectrum, typically red, green, and blue colors. But you can also have other types of images that corresponds to other parts of the spectrum. When you have channels beyond simply RGB, but there are a discrete number of channels, then they're typically called multispectral images. And then you can also have a continuous a stream of data across the channels. So for example, if you look at a single pixel, then you can have a continuous stream across different channels of the electromagnetic spectrum. And that's typically referred to as a hyperspectral image. Now, RGB images are very useful because they're very easy to acquire, very low cost, and you can quickly acquire a large number of images, store them, and process them. Multispectral and hyperspectral are also very useful, but they serve different applications. They're used typically for specific tasks where you need spectral analysis. For example, if you want to see something that's not readily visible in the visible spectrum, then these types of images would be very useful. Now, RGB images, they work by combining photodetectors that are sensitive to these 3 parts of the visible spectrum. And like I mentioned, they can be used for a large number of applications for inspections because traditionally, and even currently, the main form of assessing the condition of an asset is with an inspector that goes out and is carefully observing different parts of the bridge. And with the modern sensors that we have, it is possible to get close to the kind of fidelity and resolution that the human eye can pick up, provided you have the right cameras. And so it can then allow the inspector to document much of what they see, cracks, certainly spalling, and then also provide not only documentation, but the ability to then use that to make measurements subsequently. And we'll talk a little bit more about how that happens subsequently. And also other defects such as a fluorescence or corrosion that is visible. Now coming to these other types of sensors, multispectral, they typically capture, like I said, discrete spectral bands, and you're looking at RGB or the near infrared spectrum, and usually more than 3, but fewer than 10 bands. The spectral resolution, which is the number of these bands, is usually not sufficient to distinguish fine-scale spectral features. So these are features that vary in their response across the different parts of the spectrum. And because there's not as many bands, it's easier to process these compared to hyperspectral. These are typically used for applications such as the detection of corrosion, the detection of anything that has moisture, such as vegetation. It can also be used for the detection of delaminations. So if delaminations have a different thermal response compared to the rest of the bridge, and so multispectral data can be useful. Hyperspectral, on the other hand, has a much more higher density of resolution across these bands, and so it's more complex to process these types of data. It's much more expensive, and there's a huge amount of data that comes in, and so you need specialized equipment to be able to collect this. The main application here is detailed material quality characterization, but you can also use it for detecting specific types of corrosion and also corrosion behind coatings. Here's an example of imaging with a multispectral camera where you can see an example of an RGB image and a near infrared image. And then you can also notice on the image on the right, which is the result of processing, the locations of living vegetation, providing a different response compared to the rest of the image. Now here we have an example of the use of a hyperspectral camera. Now these images, because of the density across the bands, form a cube as opposed to just a set of matrices. And so each individual pixel is going to have some significant data behind it across the spectrums. And so this is used sort of surgically when you want to identify things such as early corrosion on steel components. And so here's an example of it being used on the Sydney Harbour Bridge. And then here is another example on a bridge where you have steel girders. And then you can see the different aspects of the deterioration that can be assessed, such as the intact coating, the coating deterioration, a delamination, and then a deteriorated coating. And then also in the second image, you can identify rust spots very precisely. Okay, I'm going to stop there and hand it over, I think, to Adriana.
Me?
Or to Anna, sorry.
There's couple slides for me now, and then Adriana.
Yes.
So follow up with the imaging. There is another way of looking at the perspective or non-destructive techniques using infrared thermography. And this technology relies on electromagnetic radiation within a specific wavelength range, considering material surface properties like absorption, transmission, reflection, as well as the volume properties, including thermal conductivity and capacity. And during the process of collecting the data, we will look at the passive or active IRT. That means that if it's a passive, that means that they utilize natural heat source like solar heating or ambient temperature changes. And if it's an active IRT, that requires external heating like halogens. Can we move to the next slide, please? To use this technology, we need some tools, and we can have us more advanced and more expensive tools, but also we can use a more simplified options such as mobile phone with simple detectable application or IRT electronic modules devices. So again, this technology is developing, and there is more opportunities to use the IRT even in the cell phones. Can you move to the next slide? At Warsaw University of Technology, one of my colleagues was using this technology to detect trapped water in the ribs of orthotropic deck. There were several spans of this deck. So in total, there was, we can say, 22 kilometers of the ribs. And in some location, the IRT show the map of different colors, right? And these colors were, we were predicting that these colors are linked to the trapped water. And during the visual inspection, we didn't see any corrosion yet outside. But after IRT inspection, we were able to identify what locations possibly had that trapped water. And those ribs that are showing with the most darker color we got the permission to open a couple of them and confirm that there were corrosion issues. So that IRT technique helped us to identify where is the issue and then confirm that with the destructive testing. Unfortunately, we cannot do anything else after you know that there will be an issue, and to confirm that we had to open it, and of course that requires repair after that. But it shows that if you have a structure that you suspect that there is an issue, and such as with the closed section, the IRT can definitely be of use. And that's just the addition to other images. And Adriana, that's your turn.
Yes. Okay. So now I'm going to talk about LiDAR, which is the tool that I have more expertise on. So LiDAR stands for light detection and ranging, and the technology uses beam of light that measures, so it quantifies the time it takes for that beam of light to touch an object or the surrounding environment and go back to the sensor. And based on that time, it can calculate the distance between the sensor and that object. So it does this in a 360-degree horizontal scope, and vertically is about 300, depending on the sensor, to create what we call a point cloud, right? To basically capture the entire surrounding of that surrounding that sensor. Here I am. Okay. So yeah, captures detailed information, basically geometric information. It cannot see through objects, so it cannot investigate, let's say box girders or anything that's enclosed. It cannot see through or inside, but it can characterize the external surface. It provides point clouds that contain X, Y, Z coordinates. So we can convert these point clouds into as is 3D models. Facilitates geometric surveying, right, and supports rehabilitation projects. So once you have this point cloud, typically the information that you have in the office is as designed or maybe as built. The 3D point cloud will get you as is. So if there's any spalling on the surface, any excessive corrosion, that would decrease the thickness of let's say steel members. All this information can be captured because it's geometry, changes in geometry. It can be captured with the LiDAR sensor. So LiDAR has 3 platforms that can be deployed on. Terrestrial laser scanning or terrestrial LiDAR, it's mounted on a tripod. It's the one that has so it has to stay stationary while collecting data, and it has a higher accuracy among the 3 platforms, and it's ideal for 3D scanning for BIM purposes. The mobile LiDAR is, so the LiDAR sensor is different in the sense that the sensor can be moving while collecting data. The accuracy of the mobile LiDAR is about 10 millimeters. The terrestrial was 1 millimeter, so it's not as accurate, but it can collect data on a much larger scale. When we talk about mobile scanning, you mount the sensor on a vehicle, and you can drive through while you collect data. And so it's, in that sense, is ideal for mapping, right, and capturing fine details, again, on that range of 10 millimeters. And finally, you have airborne LiDAR, or where you have the sensor mounted on a drone. So it is typically the same sensor that you have on the mobile for mobile scanning. It's the same one that you have for airborne scanning. So yeah, same accuracies. But because you're on a drone, now you can scan even larger, cover larger distances and larger scales among all 3 platforms. So laser scanning, the idea here is that you can combine all 3 platforms. Maybe you have terrestrial, mobile for like any specific, larger distances, and maybe aerial on areas that you can't reach, right? That terrestrial doesn't allow you to reach. You can, mount your sensor on a drone and reach to those like areas that the human do not have access through, or high, easy access. Right, and you can then combine all of these technologies or all these point clouds that you can capture with each platform and create the 3D point cloud through combining all of them. Okay, so data processing. So the first step for data processing is the improvement of station connections. So you want to make sure that you have a reference, or you can use targets, because you're going to need to capture data from several points. You're going to have to connect all those scans to create your uniform, your connected point cloud. So you want to make sure that the stations where you scan from can be connected during the data processing. So georeferencing targets is a strategy that you can use. So while you scan, you can have spheres, white spheres, or checkerboards that are detectable by the scanner. So then it knows exactly where it is in reference of those targets, and the registration process is much easier. Then the third step is cleaning noise and error control. So in the case of bridge applications, you're going to have noise coming from vehicles driving by, or like going over the bridge while you're scanning. Also from the movement of the sensor, or the movement of the bridge while you're scanning, that can also affect the quality of your point cloud. And all these errors can be denoised through the software that comes with the technologies. And then the last step would be exporting that data to create, let's say, your BIM models or whatever 3D digital model you want to create. So yeah, so this is a more detailed explanation of that step one. So this is a case study on this particular bridge, and you see how you have the two different technologies: the terrestrial in green, and then the blue are your mobile. In this case, mobile was referring to scanning from a phone. So if you know exactly where the location of your scanning is, then the registration process goes smooth. It's much neater. Then this would be an step two, the georeferencing the targets, right? Here you have how many? 6 stations, and the georeference targets refer to those stations, again, for a cleaner registration of all the scans. Right, the step 3 is the cleaning process that we talked about, denoising. So another thing that you might want to delete, let's say, from your point cloud is vegetation, right? Just to get a cleaner look at your structure, in this case, a bridge. So yeah, noise in point clouds can occur due to inaccuracies during the registration process, environmental factors, as I mentioned, from vehicles running by, and you can just go through the denoising process to eliminate all of these. Then step 4, exporting the data. So there are many formats that you can do this. You can even use just a simple CSV file, just export X, Y, and Z coordinates, or you can have X, Y, and Z also paired with RGB, so color for every single point. And because it's point-based, it's easy to measure distances, any dimensions within the point cloud. Okay, now changing to radar interferometry. So radar is similar to LiDAR in the sense that it uses so the technology emits, in this case, is electromagnetic wave to grasp the geometry surrounding the sensor. So this wave is outside of the visible spectrum, and because it's a wave and not so the LiDAR uses a single beam of light. So you can only do one point at a time. In the case of radar is a wave, so you can do multiple targets within the same wave, right? So operating in the microwave spectrum can access dynamic and static displacement. So this is why we mentioned before is ideal for like mode shape detection, like looking at the dynamics of structures. This is like the accuracy of this technology is very small, so you can reach 0.01 millimeters within 500-meter range. So it's highly accurate. And yeah, you can reach targets up to 1 kilometer away, with a trade-off in the accuracy. This is just more explanation on the technology. So it's capable of assessing multiple targets, as I mentioned, because it's a wave, utilizing frequency. Let me move this. Yeah, frequency modulated continuous wave technique. So it can detect within that same wave different targets at a time compared to LiDAR, which is typically a single target, right? Okay, so an application of radar is measuring displacements, right? So this displacement does not or time-based displacements or dynamics of the structure. It can result in a greater agility and less exposure risk for the technicians. So for you to do this with contact sensors, let's say, you would have to use multiple sensors to, let's say, at mid-span, quarter span, and even with that, you would have to mount sensors, like hundreds of sensors, to capture what the radar can do, right? So it gives you full field without having to get in contact with the bridge. So again, it's a faster data collection technique. So you could also it might require a little bit more of data processing, but in terms of data collection, these technologies are much faster than contact sensors. That's the idea. So we're going to continue with some case studies. I believe Anna or Vedhus goes next. Okay, Vedhus.
Yeah, I think it's me.
If you can speak up a little bit.
Yes. Can you hear me okay?
Yes.
Okay, so let me know if it gets soft. So thanks, Adriana, for that. I'm going to talk now about a few case studies. The first thing I'm going to do is to recap these platforms. Let me see here. I think I lost access to the screen. I think I can request control again.
You should have access now.
Okay. There we go. I'm going to motivate this case study first with a problem that the Texas Department of Transportation had. And then they put out a call for proposals for this, and we submitted a proposal, and then we've been working on this for a few years now. But the problem was that TxDOT, they wanted to use UAVs, which are unmanned aerial vehicles, to do remote inspections of bridges. And what they did is to collect a lot of data from this Rainbow Bridge, which is not too far from where I am in Houston. And they collected a lot of data. Specifically, they collected 58 gigabytes of data. But the problem was that despite all of this data of images of this bridge, they were not able to use that data to make decisions about the health of the bridge. And this highlights a critical challenge here with remote and autonomous inspections, which is the multi-scale problem. Bridges, by their nature, span large distances. And so there is a lot of spatial coverage that needs to be met if you want to collect data from the whole asset. On the other hand, defects that may endanger the life of the bridge could be very small. For example, cracks in steel bridges, they can be very small, and so they're hard to catch. And so this creates a trade-off, because if you want to cover the whole bridge, then the quickest way to do that is to be farther away from the bridge. But if you're farther away, then you're going to miss out on the details. And so we've been trying to help TechStat to come up with standardized guidelines that they can follow, or that they can recommend consultants follow when collecting data from these bridges. So I'll recap the different platforms that we've spoken about so far, and this picture here helps to show all of these technologies in one diagram. So for the bridge, depending on what part of the bridge you're trying to collect data from, you can have an unmanned system or a manned system. For unmanned systems, you can have an aerial vehicle, so that would be a UAV. You can have a surface vehicle that's operating on the water. You can have a ground vehicle that's driving either on top of the bridge or underneath the bridge, or you can have an underwater vehicle that's looking at stuff beneath the water surface. You can also have manual data collection, where you can pretty much use any of the sensors that we've looked at in both of these with both of these types of systems. And then as far as sensors go, we have RGB cameras, thermal cameras. We also have accelerometers, which can be affixed on the bridge, and this could also be done remotely with robots. You can have GPRs, LiDARs, and strain gauges. Now, with all of these platforms and sensors, we want to create a virtual representation that we can then use for decision making. And an intermediate representation here that is useful is often called a reality model. So this is processing the collected data and creating a sort of a rough as-is representation of the structure. But then we can process this to get more semantic information out of it. For example, the specific locations of specific types of components or damage. And for this, we can use deep learning and AI-based methods. And then we can build that into more usable products that we start to call digital twins. And depending on the type of information that is in that digital twin, there are different types of digital twins. For example, if we're just looking at the geometry, then that could be a BIM model or a geometric digital twin. If you're looking at a construction sequence, or you're looking at how it's changing over time, that could be a 4D digital twin. If you have all of the condition information that is visible or acquired through different sensors, annotated on top of the bridge, and that can be a condition digital twin. And if you have some structural information, then that could be a structural digital twin as well. Now, these digital twins can be used for different applications, and we call these digital services. And these differ depending on whether you're looking at new bridges or existing bridges. So for existing bridges, which is the focus of TG 5 and 5.9, there are virtual bridge inspections, where once you collect all of this data, then you can do your inspection virtually. There's structural health monitoring, digital bridge maintenance, disaster vulnerability assessment, and fatigue assessment, to name a few. And so given that there are all of these possibilities, it becomes very important when you are collecting your data to create this digital representation that you first design your data collection process to meet what your objectives are. And so for that, a first step is to determine what your objective is. And so depending on whether you want to collect data to then do a virtual inspection, you want to collect data to be able to identify specific defects, your data collection plan, of course, is going to be vastly different. And so you first have to identify a digital service. And then depending on the service that you're looking to get, you can compute the data requirements given what platforms you have at your disposal that would be needed to be able to make a decision. And then you can design the cyber-physical interface, which is what takes your physically collected data into the digital world. Once you have that design, then you can select the digital twin type and the processing method, and then you identify your reality modeling approaches. So this is it's a general framework for the design of the digital twins. And once you've designed the data collection procedure, then you can actually deploy that to collect your data and create your digital twin and avail your service. And because you are working through this in order to identify the details, then when you execute it, you can actually make good on your initial objective. And of course, this will be an iterative process, because once you actually go through the cycle, then you can see whether your objectives were met, and if not, then you can update the design that you had to further improve your outcomes. Now, when you're trying to use unmanned aerial vehicles, also there are different types that are available in the market. Depending on what your application is, there could be several constraints. For example, depending on who the asset owner is, they may have some restrictions on using certain types of drones from produced by different countries, or they may not. But also, there are every state has, in the US at least, has guidelines on how far you need to be when you are flying a drone from a bridge, depending on the amount of traffic, the speed limits on the bridge, and whether or not there's actually traffic operating on the bridge when you are flying. And so all of those things are considerations that the operator has to be really well versed with before thinking about collecting data. And so depending on the scale of the structure that you're looking at, and also the position, whether you're going above the bridge, below the bridge, next to the bridge, there can be different types of drones that can be useful. So here we have examples of tiny drones to very large ones that you can use. And if there are questions about what to use for a specific application, I'm happy to answer them. Now, the most common type of sensor that's used with a UAV is the electro-optical camera in the visible spectrum, and then also a thermal camera. And so these can be used to create reality models with photogrammetry. This is an image from Rafael's paper. I think Rafael's on the call, at least he was at the start, where he created photogrammetric reconstructions of 3 bridges in Portugal using data collected from a drone, and you can see that the fidelity of these models are fairly good, but it does take some planning in order to be able to achieve this. The other type of sensors commonly on these drones or the UAVs are thermal spectrum or the infrared spectrum cameras. And with drones, typically you're only using passive thermography, which means you're relying on ambient thermal excitation from the sun to be able to see variation in thermal responses of the bridge. And the type of defect that is most commonly identified is the delamination of concrete. And this is because there's going to be a difference in the temperature of a delaminated part because of the hollowness underneath compared to other parts of the bridge. So if you're looking at the deck, then you will typically be able to identify delaminations using thermal sensors on UAVs. Now, going back to the efficiency problem, you want to make sure you plan out your data collection based on the specific application that you're looking at. But you also want to utilize as much information as you can acquire about the bridge and the condition of the bridge while coming up with this plan. So when available, utilize past inspection data to reduce your search space. The way that we propose that this be done is to use past inspection reports. And so if you're doing the inspection of an existing bridge, then typically you will be able to get access to the most recent inspection report from the asset manager. And you can use that to identify cracks in each zone. And we have a glossary of different types of zones that are useful for the purposes of UAV path planning. And so you can reach out to me if you're interested in that information, but we'll be releasing it publicly soon as well. Then what you can do is get an estimate of the current condition of the bridge, and so this gives you a little bit more fidelity in terms of where cracks are likely to be, and you can achieve this using statistical deterioration models. And we've developed some of these models using a large number of reports for bridges in Texas, specifically for pre-stressed concrete bridges in Texas, which is the most common kind of bridge. So if you have that kind of bridge and you're trying to guess what the current condition of cracks are based on the previous inspection report, then you can use that. But even if you don't have that, you can use the data from the previous report as your guess for the current condition of the bridge. And then if you're using some of the commercially available drones, then the main two things that you're optimizing for are the gimbal angle and the distance of the drone from the bridge. Because the farther you are away, the less you'll be able to see. The closer you are, the longer it's going to take. And so we've come up with some curves based on the sensor that help you characterize the probability of missing damage. And we want to use both the probability of missing damage as well as the consequence of missing that damage to come up with the risk of doing a certain inspection flight path. For example, if you have a crack, a hairline crack on a non-structural component, the consequence of that crack may be missing that crack may be very, very low. Whereas if you have a reasonably sized crack on a structural component, that could be integral to your inspection mission, and so then the risk of missing that is going to be high. And so we've come up with a formal way of being able to tie these things together mathematically. And I won't go into those details, but I'm happy to share that with you guys. And then you can optimize for the UAV flight. And so we have a tool that can do all of these things for you. And here's an example that we did on a bridge not too far from our campus, where here we're looking at one option where the distance of the drone from the bridge is about 10 feet. And in this case, there's no risk of missing any damage, and the time to capture is going to be 55 minutes. Whereas in the second case, the distance is going to be 16 feet. The risk of missing is 25%, and the time to capture will be 30 minutes. So this is, it's just to illustrate the trade-offs here. And you can see examples of images collected from both these scenarios. In this first case, the hairline flexural crack, you can clearly see in the 10-foot image, but in the other image, it's barely visible. Whereas the shear crack, which is very critical, can be seen in both these images. And so there's a little bit more risk in the second case, but depending on the size of your bridge and how much time you have, you can take a call, with backed up by this framework as to what data you want to be collecting. Now, once you've collected that data and then you've created your reality models, then one example of an application could be an image-based inspection. So now you're using the data that you've collected to assign condition states to different members, to different elements of the bridge. So here's one example of a bridge that we collected between Houston and Austin. And we identified elements just using the images that are not in condition state 1, and you can see those here. And then we were then also able to compare with the previous inspection reports to show that we found additional elements that were not in the inspection report previously, but also all of the ones that were. And kind of moving on to the next logical step in this is if you have all of this data, then can you use AI agents to look at this data and help you make sense of it. And so we've come up with methods that where you can have an AI agent of your choice operating in this virtual environment, and we call it a virtual embodied agent. And so what the agent can do is, for a specific question, it can decide which images in your scene it wants to look at, and then come up with a detailed response, and also gives you the specific images it used to make that response. And at the moment, it's not perfect. We've evaluated it against human inspectors. So it's not perfect, but it's very good, and you can use it. You can plug in different VLMs from OpenAI or Gemini, or from or open source ones such as Gemma, and it gives you a good first draft that you can then go more deeply into and then tweak until you're happy with it. So I do want to play this, but so it allowed me to pause it, but it's not letting me play it. Let me go back. Maybe, yeah. So here what you'll see is a question, what is the condition dating of the deck? And you can see this red dot moving around, which is the agent deciding which spots to go to and looking at the images in those spots. And it's basically filling stuff into its working memory. And then it comes up with certain images that it used to give you the response, and it's gives you something about the deck, and then it's gives you something about the soffit, and it says there's no spalling in the lamination exposed rebar. None of the bays are expected. It checked 80 bays, and overall it gives it a rating of 7 because there are some minor defects. And so then you can probe it and give it more questions and say, okay, maybe you missed this, or did you check this? And it can go ahead and do that. So that's kind of where things are going as far as making these more autonomous. Now, other applications of using UAVs, in the past, we've used UAVs also to be able to measure mode shapes of vibrating bridges. And so there's this popular study that we did in almost 7 years ago now, where I used a Phantom 3 at the time. And we had these Aruco markers on this pedestrian suspension bridge, which is called the Little Golden Gate Bridge of Mahomet, Illinois. But of course, it's much smaller than the actual Golden Gate Bridge, but similar style. But it was a very good test bed for us to be able to experiment with. And what we did is, as the bridge was vibrating due to pedestrian load, we captured vibration of the bridge with the drone. And then we went in segments, and then we stitched together this information to create mode shapes of the whole bridge and also get the natural frequencies. And since that time, lots of people have worked on this type of application. The key idea is that the frequency of vibration of the drone is typically in the very low spectrum, and for the bridge, it's usually a little bit higher than that. And so as long as there's some gap between the frequency of vibration of the drone and the bridge, then you can filter out these two signals and use that to get your information about the bridge. They've also been used to get direct displacement measurements of vibrating structures. It helps if they're higher frequency ones, but if it's a really long span, then it's going to be a lower frequency, and then it may be harder to disambiguate those signals. And these days, increasingly, we're seeing drones being used to do operations on bridges, and these could be simple things such as taking readings from existing sensors. It could also be things such as affixing or installing sensors. It could be things such as spraying, different types of protectant coatings, or also for washing, for cleaning, for painting, etc. And so there are a lot of possibilities that drones can be used for in helping maintain our existing bridges. And with that, I'm going to hand it over to Anna.
Okay, can you hear me? Yes, I realize we are already after 8 p.m. on Eastern time. Maria, is it okay if I continue with a few more slides? Yes. Okay, well, thank you all for the patience, and I hope you enjoy this presentation. So a couple more application of remote inspection aspects. So this is a bridge, railroad bridge, Trias, views from different perspective. We work on this bridge between team from Porto. Diogo Ribeiro was the leader on Porto side and Portugal, and then my team, my students from Warsaw University of Technology. Okay, I request the access, but I don't. Adriana, can you move? Because I don't think I can. Oops. Or maybe I moved, so can you go back one slide? I will let you drive. I think you did okay. Yes, yes, this one. So as Vedhus mentioned, you choose the technology for the objective, what you want to achieve. And in this case, we actually want to explore some of the total station and UAVs and find out the geometry. We selected the gazette play that we wanted to focus on. We didn't expect what we would find. So that bridge is about 45 years old. It doesn't have any issues. We had the monitoring from that bridge and had, the displacement didn't drive any attention to us. But when we started to look at the geometry, we noticed that the geometry of this gazette plate looks suspicious. There is a location that the gazette plate angle go very sudden into the straight line. So that means that this is potential issue of the stress concentration. And on the technical drawings that were available, it didn't appear that this was recorded. So we were surprised because the bridge is older, it's 45 years old, but it had maintenance 10 years ago, and there was a new technical documentation prepared with that maintenance. So what we discover brought us a question, okay, how that actually may affect the performance of the bridge. And the first stage of the study was to just explore the geometry, and we found the discrepancy between the as-is geometry and as-is and the documentation. And then the next, we did the structural analysis, which we are recently working on. We did the FUE local model and global model, and we were able to look at the stress concentration. We are still working on it, so I don't have that data to be presented. But can you move to the next slide? I just want to show how we had developed the point cloud. So we had employed the total station, so LiDAR, to get close view, very steady. But then we had also a UAV with the photos collected, and we used photogrammetry. And we actually were trying to do overlap of both. because what we had discovered, the different angles from the UAVs help us to determine exact boundary of the geometry of the gazette plate, while the total station give us very detailed point cloud. And one more thing, that the total station and the UAV, both platforms, the two different technologies, provided very close matching. If you look at the green and the black line on that right side drawing, and then the technical documentation, the red one, definitely outstanding, definitely different shade. So this was very good finding for us, and then provide us a feed for a next stage of the project. Adriana, can you please move? Oh, thank you. So while the other case study is still under continuation, I want to also mention something that is maybe unique compared to other technologies that we had heard today. And this is onboard vehicle assisted technologies. I started working on this when I was working at the Transportation Technology Center in Colorado, 2012, 2014. We had set of test data in the control condition with many different vehicles, rail cars, locomotives that had multiple sensors on the cars. And through that multiple sensor of the cars, we were trying to investigate if we can see the response of the bridge. So the vehicle, track, and the bridge interaction was the focus of our study. The onboard sensors mounted on the track geometry car, so-called, there are multiple sensors, and they provide a lot of detailed information about the track performance, specifically right and left rail, any super elevation, any discrepancy between the rails, vertical position. So there's a lot of information that are used, and they are very valuable for the track. And the idea is, if those are available already, why don't we use them for evaluation of bridge performance? So on the bottom of the slide, you see example of what can be mounted on the vehicle. So there are accelerometers, lasers, ultrasonic sensor, cameras, GPS, inclinometers, many sensors at different location, different position. I was able to exercise a little bit of location of the different sensors, and we were able to move those sensors just to see if there will be other location better for our objective. But overall, those track geometry cars are equipped already, and they are already collecting the data. So the only thing is to be able to understand what is collected and how to interpret it when the vehicle is passing through the bridge. Adriana, can you move the slide, please? Thank you. So what we can do with the data is look at the response, the dynamic response of the railroad bridge under the traffic. And the big advantage of using the onboard system on the vehicle, it's allowing to collect the data not from the single bridge, but for entire line that this vehicle is passing through. So really, it's a tool that I think it's not yet at the level that we are using it, and we could probably make a big advantage of using the track geometry part. Again, this is more looking at the general behavior of the bridge, so it's not going to show us if there is a fatigue crack, but it can show us some deterioration on the approaches. It can show us the change of stiffness, and again, it can observe multiple bridges through the one run. Can we move to the next slide, please? So as I mentioned, I explored that when I was DTCI employee, 2012, 2014. We started working on the project. We continued 2016. But different cars, different systems, and different data accumulation provide us very consistent information. We were able to interpret the data, and we confirmed that those system works. So there's two publications follow up with that research, 2016, 2017, if you want to find out more details about that study. And can you please move to one slide further? So this is example of the track geometry card that we used, and this is a bridge. trust me, this is a bridge, 3-span bridge that we were able to adjust stiffness. So there was a left and right side set of beams that we could adjust. We can make less beams or more beams, and then we could identify what's the stiffness on the left and right side. We had multiple configuration. We also adjusted the approach by raising the bridge or lowering the bridge approach on the left and right side. And we had multiple runs with different speed. We tested, we collected the data, and we tried to interpret it. And there is a graph showing that we could actually finding out if there is a change of the stiffness of the one of the span, and also from the track perspective, from the locomotive and the track geometry car perspective, we were able also identify if it's a left or right side, and how much displacement was raising from the perspective of the track performance. So the vehicle-track interaction was very important to understand. Can you move to the next slide, please? Kind of follow up, but to make a most recent a field study was performed in Poland. So when I returned to Poland in 2021, we look at the same track geometry cars. Well, we look at the track geometry car that were very similar to what I experienced from data collection at TTCI. And we were able to look at the track geometry car from line of bridges. So there was no control conditions. We didn't know exactly what was going on with the bridges. So this was really like, we had this blind test. We had the data, but we didn't have any other information. So from that data, we were able to look at specific bridges, specific location, and identify that there were changes. There were changes in bridge behavior, and further investigation confirmed that there were either an issue with the approach of the bridge or a ballast condition change on the approach to the bridge. So again, a little bit different perspective in terms of the remote inspection or remote investigation of the bridge, but very promising, since this is the system that is existing. Its only thing is we had to know more information about how to detect the specific location of the beginning and the end of the bridge. And once we have identified any issues or any changes, because basically what we are looking at is changes, if we can go and actually verify if there's anything evident related to the condition of the bridge. I think that the last slide will be kind of wrapping up. So thanks so much for being with us today. I think we cover most of our experience showing you how to use the remote inspection. There are so many different technology platforms available, and these topics are growing every year. There are tens or hundreds of publications showing different application and improving the performance, the accuracy, the data collection, and data interpretation. So we show you integration of imaging, LiDAR, radar, and other technologies that provides comprehensive assessment, leading to improved safety, precise results, and control cost. And also bridge inspection that requires technologies that incorporates various platforms. Very often, one technology may not be enough. Supplementing that in what other technologies, we can get a better picture, more significant results, showing that those platforms and technologies in combination can provide you the full spectrum of the information that you are looking for. This innovation system enables engineers and inspectors to remotely monitor, diagnose, build 3D models, and manage civil engineering structures with more with remote sense, but also with a more aware system. So you are after that data collection, you are equipped with more information, the information that you can use further in different aspects. And that's be said, I think we are done with the technical contest.